Talk about what's called a power function first. Power function is just some ax to the n. And hopefully you remember what some of this stuff looks like. We don't really care about the number out front as opposed to its sign. We care about the variable. If you see something y equals x, 2x, 3x, what do you know it is? It's a line, right? It's a line. Now, if you saw an x squared, what would you know it is? A parabola. Now, I'm not so concerned about the number out front as I am the symbol out front. What's out in front of this thing? A negative. So how's the parabola open? Down. How about x cubed? It's squiggly. Is it like the x-axis or the y-axis? Nope. Next to the y-axis. It hugs the y-axis. Should be a little steeper than that one is. That one's a little too wide. And x to the fourth, which is not something you probably recall. X to the fourth itself, without anything added to it, looks just like x squared. You know, if you make a small little table here, if you take a -1, and do a -1 times a -1 times a -1 times a -1, I think that was 4 times, what do you get? You get 1. How about a 0 to the 4th power? You still get a 0. How about a 1 to the 4th power? Still get a 1. So it actually looks just like x squared for the most part. The difference is it's going to be steeper. This one has a negative in front of it, so it's just down. Now, the whole point of going over that wasn't really so much as to refresh you about what the graphs kind of look like. It was talk about a concept called end behavior. Let's look at our x to the odds. That's 3x to the first, 3x cubed. Now, they have things in common. Both of them start low and end how? High. Okay. Now both of those happen to have positive numbers in front of them as well. You see that? All right. So right underneath this slide, you'll see that. End behavior, odd degree functions, and you're supposed to use a calculator this, but I don't really care. We did it on paper. If the degree is odd and a is positive, so we're talking about something like x or x cubed or x to the 5th, whatever, they always start low and they always end high. If I was in front of the room right now, I'd take my right arm and I'd put it down and I'd put my left arm up because that's what they look like. Now, what would happen if we made this a out in front of it positive, like we had a negative x or a negative x cubed or a negative x to the 27th power, whatever? How would it start its day? Opposite of that. So it'd start high and it would end low. For the most part, with the exception of what happens near the origin, that's all the graph. You know, you guys are accustomed to it in a Zoom 6. That's a very, very little piece of what actually happens. It's where all the interesting stuff tends to happen, but it's a very, very small piece of what's really going on. The big deal is end behavior, what happens for really big values of x or really small values of x, negative values of x. Now, our even ones, we had 2 even powers. We had a square and a fourth. Those both happen to be negative. They started low and they ended how? Low. Okay, so let's talk about that one first. That's actually right there in your notes. Even degree, negative a. So something like negative x squared or negative x to the 16th, whatever. As long as the degree is even, based on what you've seen, you will always start low and you will always end low. Now the opposite of that, the constant or the coefficient out in front is positive, so we're dealing with x squared, x to the 6th, x to the 10th, whatever. But there's a positive coefficient out front. How do they start their day? High. How do they end their day? One of my students said that's his dad. So there's a lot of little bumps in between, but it's mostly on the up and up. No, not funny at all. I thought it was funny. I'll suck. All right. So graph a polynomial using transformations. I don't even know why I have mentioned in your standard form, but standard form on this thing would be negative x to the 5th plus 1. I guess that's why I have it in there. Now, the parent for this thing is x to the 5th. You guys agree with that? You know, x to the 5th ought to look a lot like x cubed. It really ought to. And if you don't believe me, we'll make a small little table. I'll actually go to negative 2, negative 1, 0, 1, and 2, even though I probably will not be able to plot the negative 2's and the 2's. If you take a 2 and you multiply it by itself 5 times, what do you get? 32. So a negative 2 to the 5th power would be negative 32. You know, the negative 1s, the 0s, and the 1s we can do pretty easy. What's a negative 1 times negative 1 times negative 1 times negative 1 times negative 1? It's still negative 1. 0, 1. So does it look a lot like x cubed? Basically the same function. Difference is it's really steeper. That's the difference. So we got the same kind of key points as x cubed. The difference is this thing just drops right off the charts on the left, and on the right it just shoots straight up. So it's basically just a steeper version of x cubed. Hopefully you see that. So this is the parent. And now we'll graph the child, the transformation. What's that plus 1 do? Yeah, this moves it up 1. What I like to do is I like to move the entire x-axis up 1. Then I would just take my 3 key points and I'd move them all up 1. Like this guy right here, the guy that was at negative 1, negative 1. Where is he now? Negative 1, 0. The origin got moved up 1. There was a point at 1, 1. Where is it now? 1, 2. But there's a reason I'm going to dash this one. It's not the final product. Why isn't the final product? Negative reciprocated thing, didn't it? Flipped it? Final product is going to be what happens when you actually do a flip. So this piece right here was the x to the 5th plus 1. Move the whole thing up. This piece right here was when you did the flip, the negative x to the 5th plus 1. That's transformation skills. Any questions about anything so far? Yay, nay? No? What's up next? Probably next to the 4th. Go ahead. There's a negative in front. Alright. This is a lot more along the lines of how I wish you guys would do things. And in fact, on your next project, you better be writing equations like this. I don't care to see a standard form equation. I like this form. What form is that in? Really? Crickets. This is vertex form. I'll give you a generic vertex form because you've done it repeatedly with lots of different things. Generic vertex form will be f of x equals a times x minus h to some power we'll call n plus k. It's a very generic form. What do h and k represent? Your vertex. A is what we call a scale factor. You can also use it as the initial slope. The deal with that initial slope is it has to be done immediately to the left and right. Like that one's got a half. That actually doesn't mean I get to rise one and run two. It really doesn't. I can only do it within the first block. Kind of interesting. You can only do it within the first block, to the right or the left. After that, it fails. It's done. It's kind of interesting, that aspect. Usually I have kids make tables just so we don't mess that up. Now, we're supposed to graph this thing using transformations. What's the parent? Parent is x to the fourth, which is basically a u, right? Probably. How are we going to shift it? Right one. Now, let me draw that parent first. Parent, if you make a small table, just have a negative 1, 0, and 1. Has the same exact key points as x squared. It's just steep. It almost shoots straight up after that. And plug in a 2, 2 to the fourth is 16. It's just steeper than x squared. That's the only difference. Now, we're going to do our shift. We're going to shift it to the right one. I don't know why I put a tick mark there. And I'm going to dash this one because it's not the final product. This is x minus 1 to the fourth power. Now down here, I have this immediately to the left and right. Within one block is the big deal. Within one unit right or left. The half is kind of a hard thing to deal with. If it was 5, it wouldn't be hard. You'd rise 5 and run 1 and be okay. It's the half that makes it a bit of a problem. I wish I had a grid. Also wish I had more space. But I don't. So I'm going to jump over here with that thing. Is everybody okay with the move to the right? No issues? It's the half that's a little bit harder to do. You can only go up a half a unit. That's all you can do. You can only go up a half a unit. Is there an easier way to do this? I wish there was a better way to explain this. It's one of the reasons I don't like teaching this technique. And I'll probably just make a table to reconfirm this. The previous transformation had a point right here at 1, 1, right? The new one has a point at 1/2, 1. Because rising half a unit and running a whole unit, isn't that the same thing as rising 1, running 2? Isn't it? And the old one had a point at 0, 1. Well, the new one has a point at 1/2, 0. So the final transformation is just a little bit wider because the initial slope is not as steep. Now, if you don't like that, it's really not that hard to make a small table. Sometimes myself, I think it's just easier to make a small table. What you got? I got X and Y confused, didn't I? Good Lord, I'm 40 years old. Sorry. You ever do that? Everybody does. Everybody does. If you don't like that idea of that being initial slope, just make a small table and reaffirm it to yourself. And it's really that simple. And you can use a storage feature on a calculator or whatever. But if you were to take a -1 and throw it in up here, you'd have a -1. Well, that's interesting. We can't use -1. We moved the thing, didn't we? Of course, that's not going to work. You know it moved. You'd use 0, 1, and 2 for your x values. You plug a 0 into that thing, you have a -1 to the 4th. What do you get? 0 minus 1 is -1. What's -1 to the 4th? 1 times a half, half. You'll get it back. You plug in 1 in here. 1 minus 1, 0. 0 to the 4th is 0 times a half. I guess you get a 0 back. Plug a 2 in here. 2 minus 1 is 1. 1 to the 4th is 1. Half of that's a half. So if you don't like the idea of that being your initial slope, you can always make little tables centered around your vertex. You'll have the rest of it. Now, what most of you will do is you'll look on your GI-84 and you'll wonder why you don't understand this stuff. You're just going to have to sit there and, if you want to understand it, do it by hand as much as possible. If you don't want to understand it, look at Slater for your homework, which I know a lot of you do, because you can't turn all that beautiful work into me and make 50s on test kids. It just doesn't work that way. There you go. Got 4 minutes. Let's talk about this one. I think we got time to talk about this slide, and then we can stop. At the very least, we can draw something here. How can functions interact with the x-axis? Well, I'm just going to draw a polynomial. This one's going to come in from up high and make it cross, bounce up, touch, bounce down, cross the y-axis, maybe jump again, go down and touch, and bump up. This should actually be a little smoother than that. There's too much curvature there. Now, there's a couple little things on here that need to be talked about. First thing I want to talk about is these intersections. I have zeros. I'm going ahead and putting a grid on here. I have zeros at -3, -1, 1, and 3. Those are your zeros. A couple of these are kind of specials. The -3 and the +1 are what we call crosses. Because they cross the x-axis. The -1 and +3 are touches because they touch the x-axis. You guys remember anything about crosses and touches? No. It has to deal with how many answers there are. If you looked at y equals x squared, a parent function, it touches the x-axis. How many zeros does it have? X squared, how many zeros does it have? How many solutions does it have to have? 2. They're repeated, but it has 2 solutions. If you look at the very simple parent function y equals x, that thing crosses the x-axis. How many solutions does it have? 1. You guys forgot about the fundamental theorem of algebra. Exponents tell you how many solutions you have. We'll start here tomorrow. Yeah, if you didn't finish that test, you need to come back and finish it today. Don't you be putting me in a bind. Asia, you're about the only one that I'll give another day on. If Allison happens to show up, tell her to come finish your test. Or if you're watching at home, finish your test.